Hello everyone, and welcome to today's live broadcast, Selecting the Right Resin to Achieve Optimal Results from High-Throughput Batch to Process Scale Protein Purification, presented by Scott Mayer and Aaron McBride, both Scientist 3, Protein Cell and Cell Analysis Life Sciences Solutions Group, Thermo Fisher Scientific. We are excited to bring you this educational webcast presented by LabRoots and sponsored by Gibco, part of Thermo Fisher Scientific. I'm Julie Simroth of LabRoots, and I'll be your moderator for today's event. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please note that you will be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. If you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window, or use the Q&A button to let us know that you're having a problem. Now, please join me in welcoming Scott Mayer and Aaron McBride. I will now turn the presentation over to them.
Thanks for the introduction. So my name's Scott Mayer, and today my colleague Aaron McBride and I will be presenting a talk on selecting the right resin to achieve optimal results from high-throughput batch to process scale protein purification. There's an increasing focus on protein research, whether it be for structure function studies, understanding interactions of a protein of interest, or the development of a potential biotherapeutic. This research requires efficient and effective isolation of pure protein at a variety of scales. Chromatography resin performance requirements can vary depending on protein characteristics and scale. Producing a quality protein while reducing costs and time without compromise in performance can be a challenge. Thermo Fisher Scientific is committed to providing flexible, high-performance beads and resins for high-throughput purification and scalable purification capabilities. Here are some of the unique purification challenges researchers might encounter on a daily basis that can hamper productivity. Researchers working in academia or industry doing small-scale purification at the milligram level may be screening different conditions for optimal purification of their protein or proteins of interest. They face the challenge of achieving optimal yield and purity with minimal purification steps and high throughput. Production scientists purifying protein at the gram level, pilot scale, are typically developing a protein for commercial purpose and are tasked with optimizing a purification process at the gram scale. They face the challenge of scaling up and achieving high yield and purity, all at a reasonable cost. A process scientist purifying kilograms of protein has a constant focus on efficiency. They're faced with the challenge of improving productivity and reducing costs of protein purification while still meeting regulatory needs. These challenges all require simplifying the process and reducing costs. Choosing the right protein purification resin will help make the process effective and efficient. So there's different base supports for chromatography and protein purification, and each one is catered to a specific application. This table shown here provides guidance on our definitions of protein purification scales and throughput needs. So for customers requiring batch purification at all throughputs, we recommend magnetic agarose. The support's ideal for automated scouting of conditions for protein purification. For batch to pilot scale, we recommend our superflow resins, which can be used either in a drip or spin column format and FPLC. This resin is very versatile and is useful for researchers requiring larger amounts of protein for structural studies, and is also useful for intermediate scale protein production at the pilot scale. For batch to process scale, we recommend our Porous Resin. This base support is geared specifically for FPLC at all flow rates and can significantly improve processing speed of bulk production. I've highlighted the different base beads we have available and what applications they are recommended for. Now I'll discuss some of the functionalities available on these supports for purifying proteins. We'll be focusing specifically on affinity chromatography as a tool for protein purification. Affinity chromatography provides a straightforward positive selection strategy for protein purification. Purification is often as simple as binding, washing, and elute. A variety of immobilized ligands are available to provide a high-fold purification with ease of use in mind, significantly reducing process optimization and variability seen with other chromatography methods such as ion exchange or hydrophobic interaction. Depending on the immobilized affinity ligand, a high level of purity and yield can be attained in a single column purification. A strategy is often implemented for the purification of recombinant proteins using a tag-based capture, and also for the purification of full-length antibody using immobilized antibody binding proteins. We'll be showcasing purification supports for tag-based affinity capture and antibody purification in this presentation. So in the first half of this presentation, I'll be focusing on affinity purification of recombinant expressed proteins, sharing data on our magnetic agarose beads and our superflow resins. Some common affinity purification strategies include immobilized metal affinity chromatography, or IMAC, for binding polyhistidine tags, and immobilized glutathione, or GSH, for binding GST fusion proteins. Polyhistidine tag protein capture utilizes immobilized tetradentate metal chelators charged with nickel or cobalt. This ligand will bind proteins tagged with multiple histidines fused at the N or C terminus of the protein. Nickel coordinated with nitrotriacetic acid, NTA, has a higher binding capacity, while cobalt is more selective, resulting in higher purity. Glutathione is a tripeptide ligand that binds GST, a 26 kilodalton N-terminal fusion, as a substrate. GST folds quickly to help with solubility of your target protein, and it can even improve expression of some harder to express recombinant proteins. Glutathione is very specific to GST, resulting in high purity eluates. This table shows all the supports for polyhistidine tagged or GST fusion recombinant protein purification available from Thermo Fisher Scientific and the applications they are recommended for. I will be highlighting advantages of magnetic agarose beads for high throughput batch purifications and superflow resins for larger scale purifications. Pierced magnetic agarose beads are highly cross-linked, providing a robust support with low nonspecific binding and a larger surface area than other polymer-based magnetic beads for a higher binding capacity. The beads, which are 10 to 40 microns in size, are easier to handle compared to other larger magnetic agarose beads and have a slower settling rate, which helps keep the beads suspended while batch binding your protein of interest. The beads are embedded with magnetite, resulting in fast collection and strong magnetic attraction. So the graph on the right shows that smaller magnetic beads have more beads left in the supernatant after collection for 10 to 60 seconds, while the pierced magnetic agarose beads have very little left in the supernatant compared to a blank without any beads, even after a short collection time of 10 seconds. And the Pierce magnetic agarose beads are available with Ni-NTA and Glutathione ligands for recombinant tagged affinity protein purification. Protein yield is an important aspect for all scales of protein purification, not just high throughput batch. So we looked at the capacities and yields of two different proteins, either His-tagged or GST fusion proteins expressed in E. coli cultures and lysed with beeper complete and then purified following recommended protocols for a variety of commercially available magnetic agarose beads. For both His-tagged and GST fusion expressed proteins, Thermo Scientific Pierce magnetic agarose beads resulted in the highest yield. Increased recovery with Pierce magnetic agarose beads reduces the cost per mg of protein purified, and it also allows for smaller volume expressions, and you'd still obtain the same amount of protein you would get when purifying with other magnetic agarose beads at higher expression volumes, thus freeing up more space on shaker platforms. Additionally, the yields obtained at this scale with Pierce magnetic agarose beads could enable studies requiring higher amounts of protein, such as functional activity measurements and even some structural analysis. A highly homogeneous product is also important for protein purification. Increased capture of target protein and low nonspecific binding is ideal for highly homogeneous purifications. Optimizing the amount of target protein to bead volume ratio will help to reduce contamination from other proteins. His-tagged Bure, Whiten ligase, and GST green ranilla were purified with various magnetic bead supports following manufacturer's protocol, and equal amounts of eluted protein were separated by SDS page and assessed for purity. The Pierce Ni-NTA magnetic agarose beads resulted in greater than 90% pure protein for His-tag purification, and Glutathione magnetic agarose beads resulted in greater than 95% purity for GST fusion proteins. Magnetic beads have traditionally been thought of having lower binding capacity than traditional agarose. Magnetic agarose provides a similar functional ligand density as traditional agarose resins. Additionally, since magnetic agarose beads have a smaller diameter than traditional agarose resins, you get a higher cumulative binding surface, which is advantageous for smaller microliter resin volume scales. We purified a variety of His-tagged and GST fusion proteins with the same volume of magnetic agarose beads and agarose resin. For the His-tag purification, Thermo Scientific Pierce Ni-NTA magnetic agarose beads perform comparably to an agarose resin in regards to yield, whereas with the magnetic agarose beads, you actually outperform glutathione agarose resin at this scale, possibly due to increased surface area and better capture at low protein concentrations. Automation is essential as sample numbers and throughput increases. Automating magnetic agarose bead protein purification is a straightforward procedure using the Thermo Scientific Kingfisher magnetic bead processor. You can see that time required for each affinity purification step is similar for automated magnetic agarose and manual agarose-based purifications. However, with the manual process using traditional agarose, you have a lot more handling steps, whereas automation allows the users to do other tasks while purification runs. Thermo Scientific magnetic agarose beads are compatible with both manual and automated protocols. For manual methods, up to 16 samples can be purified in a little over an hour. As mentioned on the last slide, higher throughput is simplified with use of the Kingfisher Flex purification system, which can process 96 samples at a time in less than 90 minutes. Pierced magnetic agarose beads perform similarly in manual or automated methods. His-tagged and GST fusion protein purifications had similar yields for manual purifications or automated purifications, and less than 5% variance between triplicate purifications on the Kingfisher platform. Here are applications in which Ni-NTA or glutathione magnetic agarose beads have been used to optimize protein purification at the high-throughput batch screening scale. So not all proteins are stable and soluble in buffers used during purification. Finding conditions in which a protein retains its native structure or does not precipitate out of solution can be arduous. An additive screen can be done at small scale to find tolerable conditions for your protein of interest. Using standard purification conditions, his-tagged biotin ligase precipitated an elution buffer after about 10 minutes of storage. Conditions were scouted to improve stability and solubility of this protein using Ni-NTA magnetic agarose beads. Addition of 20% glycerol to the binding, wash, and elution buffers significantly improved yields and solubility of his-tagged biotin ligase. Accessibility of the tag for purification can also be screened with magnetic agarose beads. Placement of the tag in quaternary structure influences binding of target protein to the affinity resin. Confirming the correct placement of affinity tags with magnetic agarose beads before doing larger scale purifications helps to prevent loss of time and money. CHO-IVT expressed C-terminal his-tag proteins were purified following manual protocol with pierced Ni-NTA magnetic agarose beads. Load, flow-through, first wash, and eluate fractions were evaluated by Western blot using an anti-His5 antibody. P53, which forms a tetramer of identical 53 kilodalton proteins, had poor binding, probably due to low accessibility of the His tag at the C-terminus. GST fusions were also screened for tag accessibility, with protein AG fusion showing poor binding. 4 of the 6 constructs screened would be ready to scale up. However, the P53 and protein AG constructs would require further optimization before scaling up. Overall, pierced magnetic agarose beads have significant benefits for high-throughput batch affinity purification of recombinant tag proteins, including high binding capacity and automation capabilities. This support is extremely versatile and can be used to rapidly and efficiently evaluate additive screening, wash conditions, tag accessibility, protein engineering, and protein-protein interactions for His-tagged or GST fusion recombinant protein. Now to talk about selecting resins for higher scale recombinant protein purification. Scaling up to the gram level pilot scale requires a resin which can tolerate high flow rates and have high specificity to decrease runtimes and chromatography steps required. Superflow resins are highly cross-linked and can tolerate up to a 0.6 megapascal back pressure and linear flow rates up to 1,200 centimeters per hour. The graph on the right shows that Superflow 6 resins tolerate flow rates significantly higher than other agarose resins before the resins start to compress. The surface of the Superflow 6 particle helps to provide high binding capacity necessary for this scale. And available resins include immobilized Ni-NTA and cobalt superflow for IMAC and immobilized glutathione for GST fusion purifications. Superflow 6 resins are ideal for column-based affinity purifications. The resin can be used in batch bind format and poured into a gravity flow column or pre-packed into an FPLC column for larger volume purifications. For FPLC purifications, the protein is loaded onto the column under flow and the binding is dynamic. Binding will be dependent on the amount of residency time the protein gets to bind to the resin. This residency time is inversely related to the flow rate. Dynamic binding capacities for His-Pure Nickel-NTA superflow, His-Pure Cobalt superflow, and Glutathione superflow are shown here. The resins all have high binding capacities. Binding capacity will be protein specific. Determining your binding capacity can be useful for further process improvement. Identifying the flow rate at which you see an inflection point in the binding capacity is a good starting point for optimal flow rate and yield in your purification process. Reusing columns packed with superflow resins is possible, generating additional cost savings. Nickel-NTA superflow resin tolerates sanitization and clean-in-place with 0.5 molar sodium hydroxide for a total of 26 runs without significant loss of performance. Cobalt superflow does not tolerate stringent clean-in-places, but typically only requires a low pH mess buffer clean-in-place. No decrease in protein yield, purity, or increase in back pressures were observed after 25 cycles. Glutathione superflow can also be reused at least 25 times with a simple guanidine HCl and ethanol clean-in-place with no significant loss in yield or purity. Additionally, with the iMac resins, very low metal leaching was observed in the elutions determined by ICP-MS. This is important since leached nickel or cobalt can lead to damage of protein. So here's a typical pilot scale run for purification of a His-tagged protein. Pilot scale purifications were conducted on 100 grams of E. coli biomass overexpressing His-tagged GFP with columns packed with either 200 mils of nickel-NTA superflow or cobalt superflow. 1 liter of total lysate was passed over the column at a flow rate of 20 mils per minute and next washed to baseline with either buffer containing 30 millimolar imidazole for nickel-NTA or 15 millimolar imidazole for cobalt. Finally, protein was eluted with 300 millimolar imidazole for the nickel-NTA column and 150 millimolar imidazole for the cobalt column, and fractions containing purified 6-X-His GFP were pooled, and protein concentration was measured using protein 660 assay. Both purification runs were completed in under 3 hours. And for this particular purification, greater than 4 grams of protein was purified with both nickel-NTA and cobalt superflow. However, the cobalt superflow resulted in greater purity. Superflow resins provide substantial benefits for batch to pilot scale purification for FPLC, including high dynamic binding capacity at high flow rates used in large scale FPLC applications. Superflow resins are available with nickel-NTA, cobalt, or glutathione ligands to enhance yield or purity. The resins have low ligand leaching and can be reused at least 25 times. In summary, our portfolio of recombinant protein purification tools provide the following benefits. Key ligands are available to meet typical purification needs. Our resins and beads are economically priced and perform well in regards to binding capacity and purity. And we have a variety of supports to accommodate all scales, allowing the user to choose the right support to optimize the recombinant protein purification. So I'll now turn things over to my colleague, Aaron McBride, who will be discussing antibody purification. Aaron?
Thanks for the introduction, Scott. Affinity resins, as Scott mentioned, can be broken down in several categories, such as tag-based purifications, immobilized antibodies, and of course, antibody purifications. For the second half of the talk, I will go over some of the chromatography resins in our portfolio that will make antibody purification workflows easier and much more efficient. Specifically, I'll talk about our Pierce magnetic Agarose beads and our Thermo Fisher Scientific Poros Mad Capture Select resins. First, we'll talk about the multiple affinity ligands used for the purification of antibodies. The classical ligands for antibody purification are either protein A or protein G. Protein A is used in the majority of antibody purifications due to its better chemical tolerance, which is useful when cleaning and reusing the resin, and antibodies that can be eluted under milder conditions. Protein A binds the CH2-CH3 interface, but can also bind the VH3 variable region, allowing it to bind some Fabs. The disadvantage of protein A is that it does not bind IgG3 and it does not bind all Fabs. Protein G, in contrast, binds at the CH2-CH3 interface, but also binds at to CH1, allowing it to bind all Fabs. In addition, protein G binds IgG3 and has poor binding to other IgG subtypes, such as IgA and IgM. The disadvantage of using protein G is that it does have lower chemical compatibility, and typically harsher conditions are needed to elute. While the majority of the purifications are binding a human or humanized IgG antibody, there's also a significant amount of purifications that deal with non-human antibodies. The specificity of protein A and protein G to non-human antibodies can vary greatly, and care should be taken when choosing ligands for a non-human antibody. In most cases, they are complementary in that if protein A does not bind or binds weakly to one species, protein G will bind strong to that species. For labs that are doing purification on a wide range of antibodies, protein AG offers an all-in-one solution. Protein AG is a chimeric protein that combines the 5 antibody binding sites of protein A and the 2 antibody binding sites of protein G for an all-in-one resin, allowing for it to handle all purification options. Within our antibody purification portfolio, we have protein A, protein G, and protein AG resins on a wide variety of base supports. For the remainder of this discussion, we'll be focused on 2 of those base supports: magnetic agarose for high-throughput batch applications, and Poros for column chromatography applications that range from milligram to kilogram quantities. As Scott mentioned previously, pierced magnetic agarose beads are a highly cross-linked 10 to 40 micron agarose bead that has been embedded with magnetite. We have then immobilized protein AG to the bead, which creates an easy handling, robust magnetic particle that has broad IgG specificity. We will now look at how the pierced magnetic agarose works in some purification studies. This data is showing that the binding capacity of protein AG magnetic agarose beads compared to both GE's protein A and protein G mag saffrose resins. As you can see from the graph on the left, the pierced protein AG magnetic agarose beads has higher IgG binding capacity than both GE's mag saffrose protein A and protein G resins across a wide variety of isotypes when using a purified IgG. In many cases, though, purification from a complex sample vastly differs from that of a purified IgG. To look at how the resins compare, using a complex sample, we prepared a purification of IgG from sera. In both human and mouse sera, the protein AG magnetic agarose beads had equivalent or higher capacity while also having a purity that is higher or equal to the competitive resin. However, one aspect of working with magnetic resins that truly makes it efficient is the magnetic supports can be automated. Here we are showing a purification of a human IgG that was expressed in our XP-CHO system. In this experiment, we were looking to identify how reproducible is a purification on an automated system. Here, for this, we performed the purification on the Kingfisher Duo system in 12 replicates. On the left, you can see a reducing and non-reducing STS page looking at the purity of the human IgG that was purified. The purity on all 12 samples were near identical. The results on the right show the total yield from each purification, and as you can see, we had a high degree of reproducibility. In summary, our pierced protein AG magnetic agarose resin is a high capacity and has a high purity IgG resin that allows for easy automation and also has a broad IgG specificity to accommodate most IgG isotypes. Next, we will discuss resins that are suitable for column chromatography. As with all the resins discussed in this talk, It is the ligand and resin combination that dictates the efficiency of your total purification, and the next resin is no exception. Thermo Fisher Scientific Porous Chromatography Bead offers this high-efficient resin for column chromatography and provides a number of highly advantageous performance features. The first is that it's made out of polystyrene divinyl benzene, so the beads are rigid and incompressible. This allows them to easily be handled, and the beads have very robust physical and chemical stability. In addition, the rigidity allows for operation at very high linear flow rates. Second attribute is the fact that they have very large pore structure, which allows for convective flow through the bead. This large pore structure unlocks the bead interior, increasing the surface area and resulting in higher capacity. Also, due to the large through pores, the beads have improved mass transfer capabilities, allowing for a more efficient bead. So you can maintain higher capacity and higher resolution independent of your operating flow rate. This leads to higher efficiency at increased linear flow rates and improves process productivity. Lastly, the beads have an average particle size of 50 microns. Most resins have an average particle size of 90 to 100 microns. Having a particle size that is roughly half the size of most other resins allow for a superior resolution. In addition, Poros is a fully scalable and possesses excellent pressure flow properties. With Poros, performance is independent of both the scale and the flow rate of your operation, which makes it an ideal purification resin. But how does it compare to typical Agarose beads? Typically, with conventional media, the pores are much smaller, so diffusion in and out of the small pores controls performance in conventional chromatography. Diffusion is regulated by residence time. The longer residence time, the deeper the molecule can penetrate the resin, and the higher binding capacity and better mass transfer you will acquire. Residence time, however, is inversely proportional to flow rate. Thus, the practical consequence is that when linear velocity increases through the column, capacity and resolution decline rapidly. Thus, you cannot speed up the process by increasing the flow rate, as it is controlled by the size, concentration, temperature, and the KD for your specific molecule. Porous chromatography resins offer a difference than traditional chromatography soft gels, in that Poros, the bead is transected by a wider through pores, which unlocks the bead interior and allows convective flow, plus much shorter and shallower diffusional pores. Since diffusional distances are reduced, mass transfer is improved, and the practical consequences that linear velocity increases through the column, capacity and resolution are minimally affected. These effects are more easily seen in looking at breakthrough curves. This slide shows customer-generated data that illustrates how breakthrough curves can be influenced by flow rates on both the Poros bead and an Agarose bead. The y-axis is the amount of IgG in the flow-through, which is C, over the amount of IgG in the load, which is C0, with a ratio of 1 equal nothing in binding and all binding sites are taken. The faster the transition from 0 to 1, the more efficient the column is. If we look at the far right line in both graphs, which is 50 centimeters per hour, we see that the perfusion media C over C0 is above 0.9 or 90%, fairly quickly after breakthrough, while Agarose barely over 60% at the same volume. If we look at the far left line in both graphs, which is 700 centimeters per hour, we see two things. One is the shape of the curve is concave, convex, which indicates pore binding, while the porous material stays convex. The other item to notice is that the distance between the slowest flow rate, the far right, and the fastest flow rate, the far left, there's clearly a large range in the Agarose material, indicating a larger change in dynamic binding capacity over the range of flow rates, while the difference between the fastest and the slow rate for the porous resin has a significantly smaller change, and thus binding capacity is minimally impacted by flow rate. This demonstrates that porous binding capacity is independent of flow rate. This is further illustrated with all of our Mad Capture Select resins. Mad Capture Select resins are all the classical antibody binding ligands, protein A, protein G, and protein AG on the porous bead. All the Mad Capture Select resins are on a 50 micron bead for the optimal performance. Since they are on the Poros bead, they maintain high binding capacity across a large range of flow rates, up to 5,000 centimeters per hour, and also have robust physical stability and low back pressure, making them an excellent choice for scaling up to the process scale. The graph on the right is showing the dynamic binding capacity of Poros MAB Capture A Select versus MAB Select over a variety of flow rates. As similar to the last slide, the binding capacity for MAB Select starts to drop off after 300 centimeters per hour, while MAB Capture A Select maintains a binding capacity across a wide range of flow rates. This is also true for our newly developed MAB Capture Protein G and AG Select resins. Poros MAB Capture G Select is setting the new standard for Protein G resins. The top graph shows dynamic binding capacity using human IgG for the new Poros MAB Capture G Select as compared to the leading Protein G resin in the market, Protein G Sephiroth 4 Fast Flow, and our historic Protein G plus Agarose resins. MAB Capture G Select maintains close to double the binding capacity when compared to Protein G Sephiroth 4 Fast Flow and maintains binding capacity over a wide range of flow rates. The lower graph shows chromatograms using either MAB Capture G Select or Protein G Sephiroth Fast Flow. These resins were loaded with either goat or human serum that contain approximately 12 mg of IgG. The graph on the lower left, you can see that MAB Capture G Select has a large elution profile, indicating a higher binding capacity than that of Protein G Sephiroth 4 Fast Flow. And on the right, you can see that MAB Capture G Select has a similar binding capacity to Protein G Sephiroth 4 Fast Flow, but has more efficient mass transfer, which allows for the protein to be eluted in smaller volumes. There's a similar story for MAB Capture AG Select. MAB Capture AG Select maintains a 5-fold higher capacity for human IgG over our older AG resin. Pure Protein AG Plus at multiple flow rates. Similar to the Protein G resins, we loaded MAB Capture G Select and Pierce Protein AG Agarose resins with the goat serum that contains approximately 12 mg of IgG. We see that MAB Capture G Select maintains higher binding capacity and also has better mass transfer. In summary, due to the Poros unique bead structure, the Poros MAB Capture Select resins allow for high binding capacity at multiple flow rates with minimal change due to the reduction of residence time. Also, due to the improved mass transfer and convective flow, the resin allows for smaller elution, which minimizes downstream purification steps. As illustrated in our previous slides, our affinity resins offer unique ligands that can meet the demands of even the most challenging protein purification. The main function of the capture step in the process is to concentrate the target protein and purify as much as possible. High-performance chromatography resins like Poros can offer benefits including high dynamic binding across a wide range of conditions, excellent cleanability, and superior resolution allowed for smaller pool volumes. Next, we will present a case study showing how Poros can decrease the overall time to purify a product and how this can lead to a lower cost of goods. Both very important as processes are scaled and move through the development. By increasing the throughput, process flexibility, and process performance, the costs associated with purification can be decreased and more productive processes can be realized, decreasing the cost of redevelopment at a later stage that can further speed the overall time to market. I will now be presenting a case study from one of our customers that switched to our Poros MAB Capture A Select resin from GE Recombinant A Fast Flow. The customer is a commercial supplier of primary and secondary antibodies to researchers, IVD, and ELISA manufacturers. They were using a conventional soft gel protein A resin, and they wanted to compare to Poros MAB Capture A Select. In this case study, the company was purifying antibodies from mouse ascites and historically have used the GE Recombinant Protein A Fast Flow for all their purifications. The challenge was to reduce processing time in order to increase throughput and move to a resin that was less expensive to help with the overall COGS. They wanted to have minimal changes to the process, and they did not want to have to change buffers or add any subsequent purification steps. For their application, only a single purification was needed. Their goals were to increase process time by at least 25% and also have the resin that was at least 25% lower in costs. This would allow them to reduce the overall costs by greater than 30%. In addition, processing time and cost of the resin, they were looking at total yield, antibody purity, as well as activity. The left chromatogram shows two identical purifications of mouse IgG from mouse ascites using either Poros Mab Capture A Select or recombinant protein A Cephro Fast Flow. The red line is the Poros Mab Capture A Select, while the blue line is the recombinant protein A Cephro Fast Flow. You notice that the elution volume for Mab Capture A Select is about 30% smaller than that of the recombinant protein A and maintains similar yield. They analyzed purity by SDS page, and they did not see any difference in purity between the antibodies purified on Poros Mab Capture A Select and recombinant protein A Cephro Fast Flow. Lastly, they tested activity, which was not shown here, but they did not detect any difference in activity between the antibodies that were purified on the two different resins. They proceeded to increase the column to a production scale and tried to exploit Porous' properties by increasing the flow rates to reduce the processing time. On the left, you can see their typical production scale protocol. When they used the Poros to its fullest advantage, they were able to achieve processing times on the right. And the result is a reduction of process time of approximately 82%, and add a reduction to the cost of the resin by greater than 30%. Using the faster time, they did not notice a difference in the activity, yield, or purity from their overall small screen testing. So they are able to achieve the same product and reduce processing time by 5-fold. This was a huge advantage to them, and they were able to significantly increase throughput for their lab. Similar results could be seen on the bioprocess scale. While we don't have a case study, we have modeled a monoclonal purification using Mab Capture A Select and Mab Select on the bioprocess scale. In this model, the total feedstock would be 10,000 liters at a concentration of 5 mg per mil and on a 308-liter column. If we look at 3 different flow rates, 200, 400, and 600 centimeters per hour, binding capacity of the resin at those flow rates, number of cycles needed to purify the entire feedstock based on the flow rates and capacity, and cumulative process time, we would see that at 200 centimeters per hour, the flow rates are about equal, and the processing, there would be no reduction in the process. If you increase the flow rates to 400 centimeters per hour and compare it to the time of the 200 centimeters per hour purification, there will be a reduction in time for both. However, the Poros Mab Capture A Select would have a greater time saving because there would have to be an extra purification performed using Mab Capture A Select due to their loss of binding capacity and the extra purification being needed. At 600 centimeters per hour, Poros Mab Capture A Select would still be able to purify the entire feedstock in 4 purification, and as such, the time reduction is significantly greater. If we model a similar scenario where we compared Mab Select, Mab Select Sure, and Mab Capture A Select, we would see significant cost savings. We looked at similar flow rates to those used in the previous model, 200, 400, and 600 centimeters per hour flow rates, number of cycles required, buffer costs, process labor costs, resin costs, and total cost per batch. One thing you notice immediately is that the majority of the cost per batch is the resin cost. The process labor cost and buffer cost is significantly lower. There would be a cost savings of approximately 30% over GE Mab Select media and 50% over the GE's Mab Select Sure using a Poros Mab Capture A Select. In summary, regardless of the scale, there is a significant performance advantage and cost savings advantage when switching to the Poros Mab Capture A Select resins. Our company has an established reputation for providing tools and resources for the high-performance affinity purification of proteins. Our broad portfolio of products manufactured at state-of-the-art facilities include a wide range of base supports and ligands at every scale. In addition, we offer global support and technical expertise for all of our purification products. If you'd like to know more information about any of our products for your protein research, feel free to take a look at our protein research tool on our website, thermofisher.com/protein purification tool. This talk has demonstrated how Thermo Fisher can provide you with the resins needed to enhance your purification workflow. And with that, we'll take any questions.
Thank you, Scott and Aaron, for that informative presentation. We will now start the live Q&A portion of the webinar. And if you have any questions you'd like to ask, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question into the box that appears on your screen, and click on the send button. We'll answer as many questions as we have time for. Let's get started. Our first question is, it's for Scott. Scott, can magnetic agarose beads be used for immunoprecipitation or co-IP experiments?
Yeah, so we've used magnetic agarose for IP and co-IP experiments. The Ni-NTA and Glutathione magnetic agarose beads also work for pull-down experiments or bait-prey evaluations of looking at binding partners. Since the beads have a lot higher binding capacity than other magnetic agarose or other magnetic beads, you would want to use lower volumes. Typically, we're using like 10 to 20 microliters of bead slurry. But and again, since the beads have a lot higher binding capacity, they're more geared for high throughput, low scale purification.
Great, thank you. The next question is for Aaron. You've talked about using Poros in packed chromatography columns for an LC. Can Poros be used in gravity flow or spin column?
Thanks for that question. So really, they can be used in spin columns. You just don't get all the benefits that go along with the porous chromatography resins. Gravity flow, however, they significantly slow down the flow rates due to their bead structure and the small particle size. So it's really not recommended for gravity chromatography.
Okay, great. The next question is, what's the best purification product for the XP-CHO and XP293 systems? And I'm not sure which of you would be best to answer that.
So we've seen that for his-tag purification of proteins secreted into XP293 or XP-CHO media, that there is some interference with the purification performance of our Ni-NTA resins. You can overcome that by dialyzing or buffer exchanging the media into recommended binding buffers. For antibody purifications, the antibody secreted into the media is directly compatible with our magnetic protein AG beads shown earlier, and it should also be compatible directly with any of our protein AG or AG supports. Which support to use is probably dependent on the volume and expression level of your system.
Thank you, Scott. The next question would be for Aaron. What type of column do you recommend for Poros map capture select resin? Do I need a high pressure column for Poros?
So due to the bead structure, again, for the Poros, it's rigid and incompressible, so you can use high pressure columns. However, you can use this typical stainless steel or glass column, and that would be perfectly sufficient. Part of the structure of Poros itself allows it to generate low back pressure, so even though that it's a smaller particle bead, you don't necessarily get a huge increase in back pressure as you typically would see in smaller beads.
Thank you so much for that answer. And we'll wrap up with one more question for Scott. You had a slide showing magnetic agarose had higher yields compared to non-magnetic agarose for Ni-NTA and glutathione small-scale purifications. Can you elaborate on why the magnetic agarose beads have better recovery?
I could postulate why. I mean, I don't know exactly for sure, but since the magnetic agarose bead has a smaller diameter, it's 10 to 40 microns in size, compared to agarose, which is anywhere from 50 to 150 microns. You have more beads in the same volume of so like a 100 microliter settled volume of magnetic agarose is going to have more beads than a 100 microliter settled volume of traditional agarose. So potentially you'd have a higher cumulative surface for your target to bind to. The nice thing about magnetic agarose and traditional agarose resins, they have similar ligand densities, so you get similar affinity or avidity with both beads. Just we have noticed, especially with the glutathione, when you have lower scale expressions on like the hundreds of microgram scale, that for whatever reason the magnetic agarose glutathione binds to GST fusions better than the larger traditional agarose bead.
Thank you. I'd like to once again thank Scott and Aaron for their presentation. I would also like to thank LabRoots and GIPCO, part of Thermo Fisher Scientific, for making today's educational webcast possible. Additional questions will be answered and published on Thermo Fisher Scientific's website. You will receive an email notification when answers are available. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through April 2018. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us. We hope to see you again soon. Goodbye.